Now, picture this. A blistering summer afternoon in the high desert. The heat is a physical weight pressing down on the landscape, and the air is filled with the high-pitched, rhythmic buzz of cicadas. If you walk toward the south-facing side of a standard suburban home, the air changes, becoming thick and shimmering with rising heat waves. Our thermal imaging camera sweeps across the glass panels of a large, modern sunroom. The screen of the camera flashes in angry, neon shades of orange and bright white, indicating a surface temperature of 135 degrees Fahrenheit on the unshaded masonry, and even higher on the exposed glass. Inside that glass room, the air is a suffocating 88 degrees. Despite the home's air conditioning compressor outside rattling and groaning under peak electrical load as it struggles to keep up. But then, the lens of the thermal camera pans just a few feet to the left, where a dense, leafy green canopy wraps completely around the western facade of the exact same sunroom. On the screen, the angry whites and oranges instantly melt away, replaced by deep, cool blues and gentle purples. The temperature of the brick wall behind that green curtain reads just 95 degrees Fahrenheit, a difference of 40 degrees on the surface, achieved without a single moving part, and without drawing a single watt of power from the grid. To the casual observer, this looks like a simple gardening project, perhaps an aesthetic choice by a homeowner with a green thumb, which drew nothing but soft chuckles and warnings from neighbors who assumed it would only rot the walls and harbor pests. But behind the quiet rustle of those leaves lies a complex, highly engineered microclimate that challenges our entire approach to modern home insulation and seasonal survival. If you are watching this from your own home, perhaps dealing with your own summer heat waves, or preparing for the winter chill, take a moment to subscribe to the channel so you do not miss our deep dives into passive survival tech. And tell us down in the comments where you are building and what the weather is like outside your window today. To understand how a living barrier can outperform thousands of dollars of mechanical cooling equipment, we have to step back and look at the fundamental engineering failure of the modern sunroom. For decades, home designers have fallen into the same thermal trap. During the mid-20th century, sunrooms and glass home extensions became incredibly popular across North America, marketed as a way to merge the comfort of the indoors with the beauty of the natural world. They were celebrated as passive solar collectors, designed to trap the gentle warmth of the winter sun and distribute it through the home. But what works beautifully in January becomes a thermal nightmare by July. When shortwave solar radiation passes through clear glass, it strikes the solid objects inside, such as tile floors, concrete foundations, or furniture. These materials absorb the energy and radiate it back out as long-wave infrared radiation. Because glass is largely opaque to long-wave radiation, that heat becomes permanently trapped inside, creating a miniature greenhouse. In a high solar radiation zone, such as the arid valleys of eastern Washington or the dry basins of Utah, an unshaded sunroom can easily reach over 100 degrees Fahrenheit inside. Even when the outdoor air is a comfortable 75, this is the classic greenhouse oven. To combat this, homeowners typically try a series of expensive, temporary fixes. They install reflective window films designed to bounce the sun's rays away before they can enter. But under the relentless bombardment of ultraviolet light, these plastic films eventually break down, becoming cloudy, blistered, and brittle within just a few seasons. Others turn to heavy interior blinds or motorized shades. Think about that for a second. Once the sunlight has passed through the glass and hit an interior blind, the heat is already inside the building envelope. The blind simply absorbs the heat and radiates it directly into the room, acting as a giant, hanging radiator. To truly stop the heat, the thermal barrier must be placed on the outside of the glass, intercepting the solar energy before it ever touches the building's envelope. Yet, conventional exterior shutters or fabric sails present their own mechanical weaknesses. They catch the wind like sails during summer thunderstorms, They require manual adjustments, and they degrade rapidly under the burning summer sun. When our homeowner first announced her plan to wrap her sunroom in dense, living vines, the reaction from those living nearby was highly skeptical. They warned of moisture being trapped against the house, of roots boring into the mortar joints of the chimney, and of a chaotic, overgrown mess that would devalue the neighborhood. Here's what everyone missed. The design was not a chaotic, wild planting, but a carefully calculated double-skin facade, engineered to balance seasonal thermodynamics with structural safety. A home is a dynamic system, and modifying its exterior envelope requires a deep understanding of structural load, moisture control, and air movement. The neighbors assumed the vines would climb directly on the walls, clawing into the siding and trapping damp air against the building's wooden frame. But that is a recipe for structural rot, mold, and catastrophic building failure. Instead, the system was built around a high-tensile steel wire trellis, offset from the building by a precise air gap. This gap allows the house to breathe, preventing moisture buildup while utilizing the physics of natural convection to carry excess heat away. The numbers don't lie. Even a modest reduction in surface temperature can lead to a massive drop in the energy required to cool a home. But achieving this balance requires more than just planting a few seeds and hoping for the best. It requires a precise assembly of materials, a strategic selection of botanical species, and a rigorous commitment to safety protocols. Let that sink in. A failure to design the system correctly could lead to collapsed structures under the weight of wet winter snow, or even deadly gas buildups if the vegetation interferes with the home's heating ventilation. To see exactly how this passive shield was constructed, and how it managed to withstand the elements while keeping the interior spaces remarkably cool, we must look at the step-by-step engineering of the trellis itself. The realization that a living, breathing shield could protect a home from intense solar radiation led directly to the drafting board, where the laws of structural engineering and botany had to be carefully woven together. To build a system that would endure for decades, the homeowner knew that relying on cheap wooden trellises or plastic netting would only lead to premature failure, rotting wood, and a collapsed canopy during the first major storm. The project began with a rigorous analysis of structural load. A mature vine canopy is not a light, decorative accent, but a heavy, dynamic mass that responds to the elements. During a summer downpour, the dense foliage absorbs water like a sponge, increasing its total weight by up to 300%. Furthermore, a strong wind blowing against a solid wall of leaves behaves exactly like a sail on a ship, exerting hundreds of pounds of lateral force against the building envelope. To withstand these intense physical stresses, the foundation of the green facade had to be anchored deep within the structural frame of the sunroom itself. The homeowner selected grade 316 stainless steel wire rope, measuring exactly 1/8 of an inch in diameter. This specific grade of stainless steel is alloyed with molybdenum, providing exceptional resistance to localized corrosion, which is critical when the metal is constantly exposed to the humid, acidic microclimate created by transpiring plants. To mount these cables, heavy-duty stainless steel standoff brackets were sourced, designed to project exactly 5 inches outward from the sunroom's exterior walls. These standoffs were not simply screwed into the siding. Every bracket was aligned with a structural wooden wall stud, pre-drilled, and anchored using 3-inch stainless steel lag screws, sealed with high-grade silicone to prevent any water intrusion into the home's framing. For the masonry sections, the brackets were secured using heavy expansion anchors set deep into the brickwork. These standoffs were spaced at intervals of 4 feet vertically, ensuring that the wire rope would not sag or whip excessively during high winds. At the top and bottom of each vertical cable run, heavy-duty jaw and jaw turnbuckles were installed. These turnbuckles allowed the homeowner to tension each cable to approximately 80 pounds of static tension, creating a rigid, drum-tight grid that would remain stable under the weight of the climbing plants. To prevent the steel cables from cutting into the soft vine tissue, and to give the young plants an easier surface to grip, natural coconut coir rope was loosely wrapped around the steel wires. This biodegradable fiber would provide an excellent grip for the initial years of growth, eventually decomposing as the vine's own woody stems matured and wrapped themselves permanently around the high-strength steel core. With the physical support system securely in place, the next critical engineering step was to protect the foundation of the home. Plants naturally seek out water, and the moisture-rich soil near a home's foundation can encourage root systems to grow toward the concrete, potentially finding tiny cracks, expanding, and causing severe structural damage over time. To prevent this, a high-density polyethylene root barrier, measuring 60 thousandths of an inch in thickness, was installed. The homeowner dug a trench 24 inches deep along the entire perimeter of the sunroom foundation, placing the plastic barrier vertically against the soil before backfilling. This simple step forces the vine roots to grow downward, deep into the subsoil, away from the home's concrete footings and drainage systems. Next came the vital process of plant selection. Many homeowners make the catastrophic mistake of planting invasive, evergreen species such as English ivy. While it looks beautiful in winter, English ivy climbs by using aerial rootlets that secrete a powerful organic glue, which actually penetrates the microscopic pores of brick mortar and wooden siding, physically digesting the materials and tearing the building apart. Instead, the design required a deciduous vine, one that would perform actively during the summer and then gracefully step aside when the seasons changed. The ideal candidate was found in the native Virginia creeper, known scientifically as Parthenocissus quinquifolia. Unlike invasive ivy, Virginia creeper climbs using small adhesive discs at the ends of its tendrils. These discs act like tiny suction cups, sticking firmly to surfaces without boring into the substrate or chemically degrading the mortar. As a native plant, it is highly resilient, requiring very little supplemental watering once established, and is naturally adapted to withstand both the intense heat of summer and the freezing temperatures of winter. Additionally, the homeowner integrated hops, or Humulus lupulus, on separate sections of the trellis. Hops are incredibly fast-growing herbaceous perennials, capable of growing up to 12 inches in a single day during peak summer. They produce a dense, overlapping leaf structure that provides exceptional shade, and they die back completely to the ground in winter, leaving the trellis entirely bare to maximize solar gain during the coldest months of the year. To nourish this living shield, a low-pressure, gravity-fed drip irrigation loop was installed at the base of the trellis, connected to a series of rainwater collection barrels. By utilizing gravity, the system remains completely off-grid, ensuring that even during a complete power failure in the middle of a heat wave, the green shield would continue to receive the moisture it needed to survive and cool the home. Once the plants were in the ground, they immediately began their slow, steady climb up the stainless steel grid, setting the stage for a dramatic transformation in the home's thermal dynamics. As the vines fully enveloped the sunroom, they began to interact with the laws of physics in ways that modern synthetic materials simply cannot replicate. To understand why this system is so remarkably effective, we must look closely at the science of thermodynamics, and specifically at the difference between sensible and latent heat. Sensible heat is the thermal energy that we can physically feel and measure with a standard thermometer. It is the kinetic energy of air molecules bouncing around, and it is what drives up the temperature inside our homes. When solar radiation strikes a standard masonry wall or glass window, nearly all of that radiant energy is converted directly into sensible heat, making the surface incredibly hot to the touch. But when solar radiation strikes a leaf, a completely different process occurs. Plants are living hydraulic pumps. They draw liquid water up from the soil through their root systems, transport it through microscopic tubes in their stems, called xylem, and release it into the atmosphere as water vapor through tiny pores on the undersides of their leaves, known as stomata. This process, known as evapotranspiration, requires a massive amount of energy. Specifically, it takes approximately 9,700 British thermal units of energy to evaporate just 1 gallon of water. Rather than allowing the sun's radiant energy to convert into sensible heat, the leaves absorb that energy and use it to drive the phase change of liquid water into vapor. The heat is literally bound up as latent heat, disappearing from our thermometers and cooling the surrounding air in the process. A single mature vine canopy can transpire up to 15 gallons of water on a hot, dry day. This is the equivalent of running a small, highly efficient evaporative cooler, completely powered by the sun itself. But evapotranspiration is only half of the thermodynamic story. The physical structure of the trellis grid itself plays an equally critical role. Because the stainless steel standoffs hold the vine canopy exactly 5 inches away from the home's siding, a highly efficient thermal boundary layer is created. The outer layer of dense green leaves absorbs up to 90% of the direct solar radiation, casting a deep, dark shadow over the actual walls of the sunroom. This means that the air trapped within that 5-inch gap remains shaded and cool. As the sun heats the outer surface of the leaves, the air directly outside the canopy begins to warm. However, the air inside the shaded gap remains cooler and therefore denser. This temperature differential triggers a fundamental law of fluid dynamics, known as the stack effect or the convective chimney effect. As the hot air on the outside of the leaves rises, it creates a gentle, low-pressure zone that draws the cooler, denser air from the ground level up through the 5-inch gap. This continuous upward flow of air acts as a natural thermal siphon, constantly sweeping heat away from the building envelope before it can conduct through the siding and into the living spaces of the home. It is a self-regulating system. The hotter the sun shines, the faster the air flows, and the more water the plants transpire, actively scaling the cooling performance to match the weather. However, introducing this level of organic density close to a residential structure introduces serious, life-threatening hazards if safety protocols are neglected. This is particularly true for off-grid homes or houses that utilize combustion appliances for heating. Carbon monoxide is an odorless, colorless, tasteless gas, and it is a silent killer. During the cooler months of spring and autumn, or in off-grid homes that rely on wood stoves, rocket mass heaters, or wall-vented propane heaters, the air intake and exhaust vents are the lungs of the home. If a dense, aggressive vine system is allowed to grow unchecked, it can easily wrap around these vents, physically blocking the flow of fresh air. When a combustion appliance is starved of oxygen, it begins to burn fuel inefficiently, producing massive quantities of deadly carbon monoxide instead of harmless carbon dioxide. If the exhaust flue is also obstructed by leaves, bird nests built within the dense foliage, or woody vine stems, that carbon monoxide will back up directly into the living spaces of the home with fatal consequences. To prevent this, the homeowner implemented a strict, non-negotiable safety perimeter. A mandatory 36-inch clear radius was established around every single combustion intake, vent, and exhaust flue. To physically enforce this boundary, solid aluminum sheet metal deflectors were mounted to the siding, creating a slick, unclimbable barrier that prevents vine tendrils from gaining a foothold near the vents. Additionally, the exhaust chimneys were fitted with heavy-duty, stainless steel spark arresters and bird screens, preventing any organic debris from falling down the flue or allowing vines to creep inside. Regular, monthly inspections are scheduled throughout the growing season to ensure that not a single leaf encroaches on this safety zone, guaranteeing that the home's heating systems can breathe freely and safely under the green shield. With the physical engineering, botanical science, and safety systems fully established, the sunroom was prepared to face its greatest challenges yet. As the seasons began their inevitable, unpredictable shift. As the system moved into its first full year of operation, the seasons prepared to put the engineering to the ultimate test. By mid-July, the summer heat wave had arrived in earnest, bringing with it a relentless sun that baked the landscape under a cloudless sky. The ambient shade temperature soared to 105 degrees Fahrenheit. Normally, an unshaded sunroom under these conditions would have transformed into a literal kiln, forcing the household to retreat behind closed doors and run their mechanical air conditioners at absolute capacity. Instead, the living shield was operating at peak performance. The mature Virginia creeper and hops vines had woven themselves into a thick, multi-layered blanket, completely shrouding the western and southern glass panels. If you stood inside the sunroom during the hottest hour of the afternoon, the change was profound. The glare of the sun was filtered into a soft, dappled green light, and the intense, radiant heat that normally stung the skin was entirely absent. Through the dense leaves, gallons of water were being drawn from the soil and vaporized into the dry air, pulling heat out of the microclimate. Below, the shaded soil remained damp and cool, feeding the natural convection chimney. The air within the 5-inch gap between the leaves and the glass was in constant upward motion, carrying away heat before it could touch the glass. Inside the sunroom, without any active mechanical cooling running, the temperature remained a highly stable and livable 76 degrees Fahrenheit, while the unshaded parts of the neighbor's brick walls directly across the street were hot enough to fry an egg. But summer is only one half of the thermodynamic year. As October arrived, the angle of the sun began to drop, and the air took on a sharp, frost-filled edge. For an engineered solar system, this is the critical transition phase. An evergreen shield would now become a liability, blocking the valuable winter sun and forcing the home's heating systems to work twice as hard to keep the space warm. But because the homeowner had carefully selected deciduous species, a natural, pre-programmed shift began to occur. As the days shortened, the plants stopped producing chlorophyll, allowing the brilliant reds, oranges, and golds of autumn to paint the facade. Within a few weeks, the leaves began to fall, blanketing the ground and exposing the bare, skeletal structure of the vines and the stainless steel trellis. Now, the low-angle winter sun could pass cleanly through the bare branches and strike the sunroom glass. The solar heater was back online. The sun warmed the dark slate floor tiles inside, storing heat that would slowly radiate back into the home long after the winter sun had set. However, this transitional period brought a sudden, unseasonable weather event that nearly destroyed the entire installation. An early Arctic front swept down from the north, bringing an unseasonably heavy autumn blizzard before the vines had fully shed their leaves. Overnight, wet, heavy snow began to fall, clinging to the remaining foliage and building up into thick, icy sheets. As the temperature plummeted to 25 degrees Fahrenheit, the weight on the trellis system began to multiply. The homeowner stood inside the sunroom, listening to the groaning of the structural frames as the wind howled outside. This was the moment of truth for the stainless steel wire ropes and turnbuckles. A poorly anchored system would have pulled clean out of the wall studs, collapsing under the immense weight of the ice and tearing away the home's siding. But the rigorous engineering paid off. The 3-inch lag screws set deep into the structural framing held firm, and the grade 316 stainless steel cables, tensioned to 80 pounds of static pressure, distributed the massive physical load across the entire facade. When the sun finally rose the next morning, the system remained fully intact, shedding the heavy snow as the bare vine branches swayed gently in the cold breeze. Once the wild weather patterns of the first year had passed, the homeowner began the meticulous process of analyzing the digital data loggers that had been running continuously. To determine if the green facade was truly a viable, off-grid cooling solution, the data had to be analyzed with absolute scientific precision, separating hyperbole from reality. Calibrated thermistors had been placed in 3 key areas, directly on the unshaded exterior brick, inside the 5-inch shaded gap behind the vines, and inside the sunroom itself. The recorded data presented a clear, fascinating picture of thermodynamic performance. Under direct sunlight, when the ambient outdoor air temperature was 105 degrees Fahrenheit, the unshaded exterior surfaces of the home reached a blistering 135 degrees. In stark contrast, the surfaces protected behind the dense vine canopy registered at just 95 degrees Fahrenheit. This represented an exceptional surface temperature reduction of 40 degrees, confirming that the leafy shield was blocking up to 90% of the sun's radiant energy. However, we must be careful to distinguish between surface radiant temperature and ambient air temperature. While the surface of the brick was 40 degrees cooler, the actual ambient air inside the sunroom did not drop by 40 degrees. The indoor temperature dropped by a highly stable 12 degrees Fahrenheit compared to the unshaded baseline, bringing the room down from an unlivable 88 degrees to a very comfortable 76. This 12-degree ambient drop was achieved purely through passive biology and structural design, without drawing a single watt of power from the grid. For an off-grid home relying on limited solar panels and battery storage, a 12-degree drop in cooling load completely changes the energy equation, preventing the need for massive, expensive generator backups. The numbers proved, beyond any doubt, that passive, biological shading is not just a cosmetic gardening hobby, but a highly effective form of climate engineering. This experiment reveals a deeper, more philosophical truth about how we build and maintain our living spaces. For nearly a century, modern architecture has relied on brute force mechanical systems to keep our homes livable. We build structures of glass and concrete, and then use massive, energy-hungry mechanical compressors to fight the natural climate outside. But this passive green shield shows that by working with the natural laws of physics and biology, we can create homes that self-regulate, warming themselves in the winter and cooling themselves in the summer. It is a reminder that the most elegant engineering solutions are often those that integrate seamlessly with the natural world, rather than trying to conquer it. Yet, we must also remain grounded in practical reality. A biological system is a living, growing entity, and it requires constant, active stewardship. Homeowners who wish to replicate this success must understand that it is not a set-it-and-forget-it project. The safety barriers around combustion intakes and carbon monoxide flues must be inspected regularly, especially before the winter heating season begins. The structural anchors must be checked for tension and wear, and the plant growth must be pruned annually to keep it from encroaching on roofing materials or window seals. If you choose to build your own green shield, select your plant species with care, anchor your supports deep into the structural framing, and respect the dangerous physics of carbon monoxide safety. With proper design, patience, and rigorous attention to detail, a living, breathing canopy can transform even the most challenging greenhouse space into a cool, sustainable oasis that endures for generations.